In this session, we will learn some commonly used methods to design the codebook in VQ system. The VQ technique usually includes the establishment of a codebook and the search of code words. The establishment of a codebook, also known as the codebook training. Code word search refers to searching for the code word with the least distortion between the codebook and the input vector for a given input vector when the codebook already exists. The primary and core problem of a vector quantization design is the design of the codebook. If there is no codebook design, the entire vector quantization system cannot be realized. The quality of the codebook directly affects the compression efficiency and the quality of the restored signal. There are two typical codebook design algorithms. K-means method is also called generalized Lloyd algorithm. GLA, which is a clustering analysis algorithm with iterative solution. The LBG, Lindy-Buzzy-Gray iteration algorithm, is a commonly used method to train the codebook, which is a generalized of the Lloyd algorithm that is derived from the K-means clustering method. How is the codebook designed? Firstly, we will present the design problem. Training sequence consists of m source vectors. We assume that the source vectors are k-dimensional. There are two problems to be solved. One is C solution to get the code vectors, each of which is k-dimensional. Another one is P solution to get the partition of the space. Assuming a squared arrow distortion measure, the average distortion could be computed. Secondly, we will solve the problems with optimality criteria. For the correct C and P solutions, there are two conditions to be required. Nearest neighbor condition says that the encoding region should consist of all vectors that are closer to than any of the other vectors. Centroid condition says that the code vector should be average of all those training vectors that are in encoding region. In implementation, we should ensure that at least one training vector belongs to each encoding region, so that the denominator in the above equation is never zero. According to the two conditions of VQ optimization, we can iteratively apply the nearest neighbor selection rule to generate a new centroid for each cell that can minimize the average distortion. This process is called the K-means algorithm or the generalized Lloyd algorithm. The basic idea of the K-means algorithm is to divide the training set into M clusters according to the two necessary optimization conditions mentioned above. Given a set of observations, x1, x2, until xn, where each observation is a d-dimensional real vector, K-means clustering aims to partition the n observations into k sets, S equals S1, S2, until Sk, so as to minimize the within cluster sum of squares WCSS, sum of distance functions of each point in the cluster to the K center. In the other words, its object is to find the minimum distortion equation. K-means algorithm is the most common algorithm, uses an iterative refinement technique. Given an initial set of K-means, the standard algorithm proceeds by alternating between two steps. Assignment step: assign each observation to the cluster whose mean yields the least within cluster sum of squares, WCSS. Since the sum of squares is the squared Euclidean distance, this is intuitively the nearest means. Mathematically, this means partitioning the observations according to the Voronoi diagram generated by the means. In the equation, where each SP is assigned to exactly one SIT, even if it could be assigned to two or more of them. Up this step, calculate the new means to be the centroids of the observations in the new clusters. Since the arithmetic mean is a least square estimator, this also minimizes the object of within cluster sum of squares, WCSS. The algorithm has converged when the assignments no longer change. There are two examples of K-means clustering algorithm. The number of clusters should be given firstly. The algorithm needs to be continuously adjust the sample classification and continuously calculate the adjusted new cluster centers step by step. Theoretically, the K-means algorithm can only converge to the local optimal value. Convergence to a local minimum may produce wrong results. In general, there are multiple such local optimal solutions. Initialization plays a very critical role in the quality of the codebook that is finally converged. A global optimization method is to set multiple sets of different initial vectors and use the K-mean algorithm to iteratively calculate them and select the codebook with the least distortion. Therefore, it is very important to find a suitable initial codebook. The LBJ iterative algorithm is a commonly used method to train the codebook. The LBJ algorithm computes a codebook with a local minimum average distortion for a given training set and a given codebook size. It is similar to the K-means method in data clustering. Before the beginning, the number of code words or the size of the codebook is determined. The first step is to initialize the codebook and the code words, which can be designed with different methods, with or without the training set. Then, the distance measure is used to clusterize the vectors around each code word. This can be done by taking each input vector and finding the Euclidean distance between it and each code word. The input vector belongs to the cluster of the code word that yields the minimum distance. After that, the new set of code words will be computed. This can be done by obtaining the average value of each cluster. The iteration continues until the relative distortion is less than the given threshold. There are some approaches for setting the initial codebook. The first method is randomly selecting M vectors from the training sequence as the initial code word to form the initial codebook, which is a random selection method. Some atypical vectors may be selected as code words, which are not representative. That is, the selected code words are not uniformly distributed in the training sequence. It will cause the cells to be divided too finely in some spaces and too large in some spaces. In this way, the limited code words in the codebook are not fully utilized, and the performance of the vector quantizer is deteriorated. Splitting training is utilized to avoid divergent calculation that is caused by improper selection of the initial codebook. Consider the codebook size as m equals 1. That is, the initial codebook contains only one code word. Calculate the centroids of all training sequences and use this centroid as the first code word, I equals 0. Then split it. At this time, the codebook contains two elements. One is I equals 0 and the other is I equals 1. The codebook is designed with the training sequence according to m equals 2. The two code words of this codebook are divided into two separately, and then there are 4 code words in the codebook. This process is repeated, and after designs with the log of m to base 2, the required initial codebook with m code words is obtained. The initial codebook performance of the splitting approach makes better vector quantizer with the codebook. However, with the increase of code words in the codebook, the amount of calculation also increases rapidly. That's all for this session. See you next session.